A structure bonding presentation. This is an answer to question 3 by George Fox. Any references, citations, or links to images used will be in the final slide. I hope you enjoy. Part 1. IUPAC naming. IUPAC is a worldwide naming system used for chemical compounds. Part 1 requires the correct naming of compound Z. Initially, compound Z has been given to us in its skeletal formula. These are quick to draw and nice to look at, however they require some assumptions to be made, which can cause mistakes when naming the molecule. For this reason, I'll be redrawing compound Z in a more detailed way. This allows us to see all the atoms involved as well as functional groups and bonds, making the naming process easier. Taking the newly drawn structure from the previous slide, we can now begin to identify carbon chains to help with naming. In this case, there are 2 chains with 4 carbons to choose from. Once this is chosen, we can number these carbons 1 through 4. This allows us to identify where functional groups are placed in relation to the chain, which in turn helps us name the molecule. As you can see, a methyl group is the only relevant functional group on the chain aside from hydrogens. This is placed on the second carbon, so it's 2-methyl as a prefix, and the 4 long carbon chain identifies it as butane. So the final name for this molecule is 2-methylbutane. Two-methylbutane can also be named methylbutane and isopentane. Although less descriptive due to the lack of numbering, methylbutane gives the same compound as our answer, a methyl group on a 4-carbon chain. If the methyl group is on carbons 1 or 4, the molecule is no longer butane but pentane, as it's a 5-carbon long chain. If it's on carbons 2 or 3, that carbon takes priority and automatically becomes 2-methyl. Thus, methylbutane is interchangeable with 2-methylbutane. Isopentane used to be accepted as a relevant answer. Since 2013, it's no longer accepted. Part 2 of question number 3 was based on Newman projections. These are the 6 Newman projections available for the molecule 2-methylbutane while looking along the C2-C3 bond. The second carbon will be displayed as the front ring, and carbon number 3 will be hidden as the background ring. We'll be rotating carbon number 3. The first conformation available is eclipsed, or syn-periplanar, as the methyl groups eclipse one another. The brackets in my diagrams will indicate that the atom or atoms are attached to the C3 in the background, whereas the molecules outside of the brackets will indicate they are on the front ring, C2. If we rotate the third carbon by 60 degrees, we reach our second conformation, which is staggered. This has gauche interactions as the methyl groups, the larger constituents, are next to one another. A further 60-degree rotation gives us the third conformation. Again, this is eclipsed as the methyl groups eclipse one another. 60-degree rotation further gives me a staggered conformation, otherwise known as anti-periplanar, as the methyl groups are opposite one another but in the same plane of the page on carbons 2 and carbon 3. The pattern continues for the next 2 60-degree rotations and the next 2 conformations, giving us an eclipsed and a staggered accordingly. As you can see, we now have 6 conformations that have rotated a total of 300 degrees from the one that we started with. This then means a final 60-degree rotation will return conformer number 6 to conformer number 1, from staggered back to eclipsed. As it's a rotation, there are an infinite number of possible conformations that can be drawn. However, we have chosen 6 finite conformations staggered at 60-degree rotations. Part 3 of question number 3 involves plotting the relative energy of each of the conformations of 2-methylbutane on a graph against the angle of internal rotation. In this graph, we can clearly see that there are 3 conformations of much lower energy than the other 3. The staggered conformations are the ones that pose the lower energy than the eclipsed. This is due to minimal repulsion amongst the substituents. This means that conformers number 4 and conformers number 6, displayed at 60 degrees and 300 degrees accordingly, have the same energy and a slightly lower energy than conformer number 2, which is shown at 180 degrees. This is because the conformer shown at 180 degrees has gauche interactions between its methyl groups. There are only 60 degrees between each of the methyl groups, whereas in conformers number 4 and 6, there are 60 degrees and 180 degrees between said methyl groups. This not only makes the molecule have a lower energy, but also makes it more stable. Moving on to the eclipse conformations, they have much higher relative energies due to the repulsions between overlapping constituents. Conformations number 3 and 1 have a slightly higher energy than conformation number 5, shown at 360 degrees, as they involve large repulsions between eclipsing methyl groups. By large, I mean these repulsions are much higher than the repulsions between a methyl group and a hydrogen, or 2 hydrogen atoms eclipsing one another. Conformer number 5 does not have any eclipsing methyl groups, thus poses a lower energy and is more stable. If you follow the line of the curve, similar to the pattern in the previous slide, you can see that we start with a staggered conformation, move to an eclipsed, then a staggered, to an eclipsed, then a staggered, then finally back to an eclipsed. And it will continue if the graph went on to 420 degrees, 480, and so on. You may have noticed I have not labelled a conformation at 0 degrees. This is because conformer number 5, which is labelled at 360 degrees, is identical to the one that would be posed at 0 degrees. If we were to identify the increase in energy of these conformations, we would have conformations 4 and 6 displayed at 60 degrees and 300 at a slightly lower energy than conformer 2 displayed at 180 degrees, which is of slightly lower energy than conformer number 5 at 360 degrees, which is of slightly lower energy than conformers 3 and 1 shown at 120 and 240 degrees accordingly. If you take this order and invert it, you have the order of stability of the 6 conformations of 2-methyl butane. Thank you for listening.